Today I'm gonna read the chapter Alkene from the book of Organic Chemistry by P. Bruce. Chapter 5 Alkene Structure, Nomenclature, and an Introduction to Reactivity, Thermodynamics, and Kinetics. Some of the things you will learn about in this chapter are how the Kelvin temperature scale got its name, how trans fats gets into our food, why carrots and flamingos are orange, how insects populations can be controlled, and how compounds in biological systems recognize each other. In chapter 3, we saw that alkenes are hydrocarbons that contain only carbon-carbon single bonds. Now we will take a look at alkenes, hydrocarbons that contain carbon-carbon double bond. Alkenes play many important roles in biology. For example, ethane, CH2 double bond CH2. The smallest alkene is a plant hormone, a compound that controls growth and other changes in the plant's tissue. Among other things, ethene affects seed germination, flower maturation, and fruit ripening. Many of the flavors and fragrances produced by plants also belong to the alkene family. We will begin our study of alkenes by looking at their structures and how they are named. Then we will examine a reaction of an alkene, paying close attention to the steps by which the reactions occurs and the energy changes that accompany them. You will see that some of the discussions in this chapter revolves around concepts with which you are already familiar, whereas some of the information is new and will broaden the foundation of knowledge that you will be building on in subsequent chapters. Pheromones. Insects communicate by releasing pheromones, chemical substances that other insects of the same species detect with their antennae. Many of the sex, alarm, and trail pheromones are alkenes, are synthesized from alkenes, interfering with an insect's ability to send and receive chemical signals. Is an environmentally safe way to control insect populations. For example, traps containing synthetic sex attractants have been used to capture crop destroying insects such as the gypsy moth and the boll weevil. 5.1 Molecular formula and the degree of unsaturation. We saw that the general molecular formula of a non-cyclic alkane is CnH2n plus 2, and that the general molecular formula for a cyclic alkane is CnH2n. Because the cyclic structure reduces the number of hydrogens by 2, the general molecular formula of an acyclic alkene is also CnH2n. Because the alkene's double bond causes it to have 2 fewer hydrogens than an alkane with the same number of carbons. Thus, the general molecular formula for a cyclic alkene must be CnH2n minus 2. Therefore, the general molecular formula for a hydrocarbon is CnH2n plus 2 minus 2 hydrogens for every pi bond or ring in the molecule. The total number of pi bonds and rings is called the compound's degree of unsaturation. Thus, C8H14, which has 4 fewer hydrogens than a acyclic alkane with 8 carbons, has 2 degree of unsaturation. Therefore, we know that the sum of the compounds pi bonds and ring is 2. Because alkanes contain the maximum number of CH bonds possible, that is, they are saturated with hydrogen, they are called saturated hydrocarbons. In contrast, alkenes are called unsaturated hydrocarbons because they have fewer than the maximum number of hydrogens. 5.2 The nomenclature of alkenes. We saw that the IUPAC system uses a suffix to denote certain functional groups. The double bond is the functional group of an alkene. Its presence is denoted by the suffix "ene". Therefore, the systematic IUPAC name of an alkene is obtained by replacing the "ane" ending of the corresponding alkane with "e" and "e". For example, a 2-carbon alkene is called ethene and the 3-carbon alkene is called propene. Ethene also is frequently called by its common name, ethylene. Most alkene names need a number to indicate the position of the double bond. The 4 names above do not, because there is no ambiguity. The IUPAC rules you learned in section 3.3 and 3.6 apply to alkenes as well. First, the longest continuous chains that contain the functional group. In this case, the carbon-carbon double bond is numbered in the direction that gives the functional group suffix the lowest possible number. For example, 1-butene signifies that the double bond is between the first and second carbon of butene. 2-hexene signifies that the double bond is between the second and the third hexene. Notice that 1-butene does not have a common name. You might be tempted it to call butylene, which is analogous to propylene for propene. Butylene, however, is not an appropriate name because it could signify either 1-butene or 2-butene, and a name must be unambiguous. Recall that the stereoisomers of an alkene are named using a cis or trans prefix. Second, for a compound with 2 or more double bonds, the Ne ending of the corresponding alkane is replaced by diene, triene, tetraene, and so on, depending on the number of double bonds in the parent hydrocarbon. Third, the name of the substituent is stated before the name of the longest continuous chain that contains the functional group, together with a number to designate the carbon to which the substituent is attached. Notice that if a compound's name contains both a functional group suffix and a substituent, the chain is numbered so that the functional group suffix gets the lowest possible number. Fourth, if a chain has more than one substituent, the substituents are stated in alphabetical order using the same rules of alphabetizing discussed in section 3.2. Then the appropriate number is assigned to each substituent. 5. If counting in either direction results in the same number for the functional group suffix, the correct name is the one containing the lowest substituent number. For example, the compound shown below on the left is 4-octene. Whether the longest continuous chain is numbered from the right to left or from left to right. If you number from left to right, then the substituents are at the position 4 and 7. But if you number from right to left, they are at the positions 2 and 5. Of those 4 substituent numbers, 2 is the lowest, so the compound is named 2,5-dimethyl-1,4-octene. 6. A number is not needed to denote the position of the double bond in a cyclic alkene because the ring is always numbered so that the double bond is between carbon 1 and 2. To assign numbers to any substituent, count around the ring in the direction clockwise or counterclockwise and puts the lowest number into the name. Notice that 1,6-dichlorocyclohexane is not called 2,3-dichlorocyclohexane because the former has the lowest substituent number 1, even though it does not have the lowest sum of substituent numbers 1 plus 6 is equal to 7 versus 2 plus 3 is equal to 5. 7th, if counting in either direction leads to the same number for the alkene functional group suffix and the same lowest number or number for one or more of the substituents, then ignore those substituents and choose the direction that gives the lowest number to one of the remaining substituents. Remember that the name of a substituent is stated before the name of the parent hydrocarbon and that a functional group suffix is stated after the name of the parent hydrocarbon. The sp2 carbon of an alkene are called vinylic carbons. An sp3 carbon that is adjusted to a vinylic carbon is called an allylic carbon. A hydrogen bonded to a vinylic carbon is known as vinylic hydrogen, and a hydrogen bonded with an allylic carbon is known as allylic hydrogen. The group containing a carbon-carbon double bond are used in common names, the vinylic group and the allylic group. The vinylic group is the smallest possible group that contains a vinylic carbon, and the allylic group is the smallest possible group that contains an allylic carbon. When vinyl or allyl is used in a name, the substituent must be attached to the vinylic or allylic carbon respectively. Notice how these groups are some others and some others can be used as substituent names in systematic nomenclature. 5.3. The structure of alkenes. Alkenes have structure similar to that of ethene, the smallest alkene, whose structure was described in section 1.8. Each double-bonded carbon of an alkene has 3 sp2 orbitals. Each of these orbitals overlap an orbital of another atom to form a sigma bond, one of which is one of the bonds in the double bond. Thus, the sigma bond of the double bond is formed by the overlap of an sp2 orbital of one carbon with an sp2 orbital of the other carbon. The other bond of the double bond is an pi bond, formed from side to side overlap of the remaining p orbital on each of the sp2 carbons. Because 3 points determining a plane, each sp2 carbon and the two atoms singly bonded to it lie in a plane. In order to achieve maximum orbital-orbital overlap, the two p orbitals must be parallel to each other. For the two p orbitals to be parallel, all 6 atoms of the double bond system must be in the same plane. 5.4 How an organic compound reacts depends on its functional group. There are millions of organic compounds and more being made each year. If you had a memorize how each and of them reacts, studying organic chemistry would not be very pleasant experience. Fortunately, organic compounds can be divided into families, and all the members of the family react in the same way. The family to which an organic compound belongs is determined by its functional group. The functional group determines the kinds of reactions a compound undergoes. You are already familiar with the functional group of an alkene, the carbon-carbon double bond. All compounds with a carbon-carbon double bond reacts in the same way, whether the compound is a small molecule such as ethene or a large molecule such as cholesterol. A table of common function group is located inside the back cover of this book. What makes learning organic chemistry even easier is that all the families can be placed in one of 4 groups, and all the families in a group react in the similar ways. We will start our study of reactions by looking at the reactions of alkenes, a family that belongs to the first of the 4 groups. We will revisit these groups each time we finish studying the reactions of all the families in particular group. 5.5 How alkenes react. Curved arrows show the flow of electrons. When you study the reactions of a particular functional group, you need to understand why the functional group reacts the way it does. It is not enough to look at the 2 reactions shown in section 5.4 and see that the carbon-carbon double bond reacts with the HBr to form a product in which the H and Br atoms have taken the place of the pi bond. You need to understand why the reactions occur. If you understand the reason for each functional group's reactivity, you will be able to look at an organic compound and predict the kinds of reactions it undergoes. In essence, organic chemistry is all about the interaction between electron-rich species and the electron-deficient species. These are the forces that make the chemical reactions happen. So each time you encounter a new functional group, remember that the reaction it undergoes can be explained by a very simple rule. Electron-deficient species are attracted to electron-rich species. Therefore, to understand how a functional group reacts, you must first learn to recognize electron-deficient and electron-rich species. Electrophiles. An electron-deficient species is called an electrophile. Literally, electrophile means electron-loving. Phile is the Greek suffix for loving. An electrophile looks for a pair of electrons. It is easy to recognize an electrophile. It has either a positive charge, a partial positive charge, or an incomplete octet that can accept electrons. H positive, CH3, CH2 positive, BH3 and HBr. These all are electrophiles. Nucleophiles. An electron-rich species is called nucleophile. A nucleophile has a pair of electrons it can share. Nucleophiles and electrophiles attract each other like negative and positive charges. Because nucleophiles have electrons to share and electrophiles are seeking electrons. Thus, the preceding rule can be restated as nucleophiles react with electrophiles. OH negative, Cl negative, H2O, these all are nucleophiles. In section 2.12, you saw that the Lewis acids are compounds that accept a share in a pair of electrons, and Lewis bases are the compounds that donate a share in a pair of electrons. Thus, electrophiles are Lewis acids and nucleophiles are Lewis bases. So, saying that an electrophile reacts with a nucleophile is the same as saying that the Lewis acid reacts with a Lewis base. Because the Lewis definitions are so broad, we will use the term base when a Lewis base reacts with a proton and nucleophile when it reacts with something other than a proton. This is an important distinction because base strength is a thermodynamic property and nucleophilic strength is a kinetic property. The mechanism of reaction. Let's now see how the rule nucleophiles react with electrophiles. Allows us to predict the characteristic reaction of an alkene. We saw that the pi bond of an electron consists of a cloud electron above and below the sigma bond. As a result of these clouds of electrons, an alkene is an electron-rich molecule. It is nucleophile. Notice the relatively electron-rich pale orange area is the electrostatic potential maps for cis and trans 2-butene. We have also seen that the pi bond is weaker than a sigma bond. The pi bond, therefore, is the bond that is most easily broken when an alkene undergoes a reaction. For these reasons, we can predict that an alkene will react with an electrophile, and in this process, the pi bond will break. Thus, if a reagent such as hydrogen bromide is added to an alkene, the alkene, a nucleophile, will react with the partially positively charged hydrogen, an electrophile of hydrogen bromide. The product of the reaction will be a carbocation. In the second step of the reaction, the positively charged carbocation and electrophile will react with the negatively charged bromide ion, a nucleophile, to form an alkyl halide. The step-by-step description of the process by which reactants, in this case an alkene plus HBr, are changed into products, an alkyl halide, is called the mechanism of the reaction. We use curved arrows to help us understand a mechanism. First, curved arrows are drawn to show how the electrons move, a new covalent bonds are formed and existing covalent bonds are broken. Second, each arrow represents the simultaneous movement of two electrons, an electron pair, from a nucleophile at a tail of the row towards the nucleophile at the point of the arrow. Third, the tail of the arrow is positioned where the electrons are in the reactant. The tail always starts at a lone pair or at the bond. Fourth, the head of the arrow points to where these same electrons end up in the product. The arrow always points at an atom or a bond. Fourth, the tail of the arrow is positioned where the electrons are in the reactant. The tail always starts at a lone pair or at a bond. Fourth, the head of the arrow points to where these same electrons end up in the product. The arrow always points at an atom or a bond. For the reaction of 2-butene with HBr, an arrow is drawn to show that the two electrons of the pi bond of the alkene are attracted to the partially positively charged hydrogen of HBr. The hydrogen is not immediately free to accept this pair of electrons because it is already bonded to the bromine, and hydrogen can be bounded to only one atom at a time. However, as pi electrons of the alkene move towards the hydrogen, the HBr bonds break with bromine, keeping the bonding electron. Notice that the pi electrons are pulled away from one sp2 carbon but remain attached to the other. Thus, the two electrons that originally formed the pi bond now form a new sigma bond between carbon and the hydrogen from HBr. The product is positively charged because the sp2 carbon that did not form the new bond with hydrogen has lost a share in an electron pair, the electrons of the pi bond. In the second step of the reaction, a lone pair on the negatively charged bromide ions form a bond with a positively charged carbon of the carbocation. Notice that in both steps of the reaction, a nucleophile reacts with an electrophile. Solely from the knowledge that the nucleophile reacts with an electrophile and a pi bond is the weakest bond in an alkene, we have been able to predict that the product of the reaction is 2-bromobutane. The overall reaction involves the addition of 1 mole of HBr to 1 mole of the alkene. The reaction therefore is called an addition reaction because the first step of the reaction is the addition of an electrophile to the alkene. The reaction is more precisely called the electrophilic addition reaction. Electrophilic addition reaction are the characteristic reactions of alkenes. At this point you may think that it would be easier just to memorize the facts that 2-bromobutane is the product of the reaction without trying to understand the mechanism that explains why 2-bromobutane is the product. However, you will soon be encountering a great many reactions and you will not be able to memorize them all. It will be much easier to learn a few mechanisms that are based on similar rules than to try to memorize thousands of reactions. And if you understand the mechanism of each reaction, the unifying principles of organic chemistry will soon be clear to you, making mastery of the materials much easier and a lot more fun. The reaction coordinate diagram describes the reaction pathway. The mechanism of a reaction, such as the one shown on page number 199 to describes the step known to occur as reactants are converted to products. A reaction coordinate diagram shows the energy changes that take place in each of these steps. In a reaction coordinate diagram, the total energy of all the species is plotted against the process of the reaction. Because the reaction progresses from left to right as written in a chemical equation, the energy of the reactants is plotted on the left hand side of the x-axis and the energy of the products is plotted on the right hand side. A typical reaction coordinate diagram is shown in the figure 5.1. It describes the reaction of AB with C to form A and BC. Remember that the more stable the species, the lower its energy. As the reactants are converted to products, the reaction passes through a maximum energy state called a transition state. The structure of the transition state is between the structure of the reactants and the structure of the products. As reactants are converted to products, bonds that break and bonds that are formed are partially broken and partially formed in the transition state. Dashed lines are used to show partially broken or partially formed bonds. The height of the transition state, the difference between the energy of the reactants and the energy of the transition states, tells us how likely it is that the reaction will occur. If the height is too great, the reactants will not be able to convert it to products, so no reaction will take place. 5.6 Thermodynamics. How much product is formed? To understand the energy changes that take place in the reactions, such as the addition of HBr to an alkene, you need to understand some of the basic concepts of thermodynamics, which describe a reaction at equilibrium, and kinetics, which explains the rate of the chemical reactions. Consider a reaction in which Y is converted to Z. The thermodynamics of the reactions tells us the relative amounts of reactants Y and products Z present when the reaction has reached equilibrium, whereas the kinetics of the reactions tells us how fast Y is converted to Z. Thermodynamics is the field of chemistry that describes the properties of a system at equilibrium. The relative concentrations of reactants and products at equilibrium can be expressed by the equilibrium constant Keq. A plus B is in equilibrium with C plus D. K equilibrium is equal to concentration of product divided by concentration of reactants is equal to concentration of C multiplied by concentration of D divided by concentration of A multiplied by concentration of B. The relative concentrations of products and reactants are at equilibrium depends on the relative stabilities. The more stable the compound, the greater its concentration at equilibrium. First, if the products are more stable, have a lower free energy than the reactants, there will be a higher concentration of products than reactants at equilibrium. So, K equilibrium will be greater than 1. Second, if the reactants are more stable than the products, there will be a higher concentration of reactants than products at equilibrium. So K equilibrium will be less than 1. Now you will understand why the strength of an acid is determined by the stability of its conjugate base. As the base becomes more stable, the equilibrium constant for its formation becomes larger, and the larger the Ka, the stronger the acid. Gibbs free energy change. The difference between the free energy of the products and the free energy of the reactants under standard conditions is called the Gibbs free energy change, or delta G naught. The symbol naught indicates standard conditions, which means that all the species are at concentration of 1 molar and a temperature of 25 degrees Celsius and a pressure of 1 atmosphere. Delta G naught is equal to free energy of the products minus free energy of the reactants. From this equation, we can see that delta G naught will be a negative if the products have a lower free energy, are more stable than the reactants. In other words, the reaction will release more energy than it consumes. Such a reaction is called an exothermic reaction. If the products have a higher free energy, are less stable than the reactants, delta G naught will be positive and the reaction will consume more energy than it releases. Such a reaction is called an endergonic reaction. Notice that the terms exergonic and endergonic refers to whether the reaction has a negative delta G naught or a positive delta G naught. Do not confuse these terms with exothermic and endothermic which we will define later in this section. A successful reaction is one in which the products are favored at equilibrium. That is, the products are more stable than the reactants. We saw that whether the reactants or products are favored at equilibrium can be indicated by the equilibrium constant or by the change in the free energy. These two quantities are related by the equation delta G naught is equal to minus RT in log equilibrium constant, where R is the gas constant and T is the temperature in kelvins. The Kelvin scale avoids negative temperatures by assigning 0 Kelvin to minus 273 degrees Celsius, the lowest temperature known. Thus, because K is equal to degree Celsius plus 273, 25 degrees Celsius, enthalpy and entropy. The Gibbs standard free energy change G naught has an enthalpy H naught component and an entropy delta S naught component. T is the temperature in kelvins. Delta G naught is equal to delta H naught minus T delta S naught. Enthalpy is the heat given off or the heat consumed during the course of a reaction. Heat is given off when bonds are formed and heat is consumed when bonds are broken. Thus, delta H naught is a measure of the energy of the bond making and bond breaking process that occurs as reactants are converted to products. Delta H naught is equal to heat required to break bonds minus heat released from forming bonds. If the bonds that are formed in a reaction are stronger than the bonds that are broken, more energy will be released in the bond forming process than will be consumed in the bond breaking process, and delta H naught will be negative. A reaction with a negative delta H naught is called an exothermic reaction. If the bonds that are formed are weaker than those that are broken, delta H naught will be positive. A reaction with a positive delta H naught is called an endothermic reaction. Entropy is the measure of the freedom in a system, restricting the freedom of the motion of a molecule, decreasing its entropy. For example, in a reaction in which two molecules come together to form a single molecule, the entropy of the product will be less than the entropy of the reactant, because two separate molecules can move in ways that are not possible when they are bound together in a single molecule. In such a reaction, delta S naught will be negative. In a reaction in which a single molecule is cleaved into two separate molecules, the products will be greater freedom of motion than the reactant, and delta S naught will be positive. Delta S naught is equal to freedom of motion of the products minus freedom of motion of the reactants. We saw that the favorable reactions has a negative delta G naught. The expression for the Gibbs standard free energy changes show that negative values of delta H naught and positive values of delta S naught contributes to make delta G naught negative. In other words, the formation of the products with stronger bonds or greater freedom of motion causes delta G naught to be negative, and therefore the reaction to be a favorable one. Notice that the entropy terms in temperature dependent and therefore becomes more important as the temperature increases. As a result, a reaction will be a positive delta S naught, may be endergonic at low temperatures but exergonic at high temperatures. 5.7. Increasing the amount of product formed in a reaction. Fortunately, there are ways to increase the amount of product formed in a reaction. Fortunately, there are ways to increase the amount of product formed in a reaction. Le-Chatelier's principle states that if an equilibrium is disturbed, then the system will adjust to offset the disturbance. In other words, if the concentration of C and D is decreased, then A and B will react to form more C and D in order to maintain the value of the equilibrium constant. The value of a constant must be maintained, that is why it is called a constant. A plus B is an equilibrium with C plus D. Equilibrium constant is equal to concentration of C into concentration of D divided by concentration of A into concentration of B. Thus, if a product crystallizes out of a solution as it is formed, or if it can be distilled off as a liquid or driven off as a gas, the reactants will continue to react to replace the departing product in order to maintain the relative concentrations of products and reactants, that is, to maintain the value of the equilibrium constant. Additional product can also be formed if the equilibrium is disturbed by increasing the concentration of one or more of the reactants. Living organisms obtain energy by carrying out a series of sequential reactions that convert complex nutrient molecules, such as glucose, into the simple molecules. Such a series of reaction is called a metabolic pathway. Some of the reactions in a metabolic pathway are endergonic and therefore produce very little product. However, the amounts of product produced is increased if the endergonic reaction is followed by a highly exergonic reaction. Another application of Lesch-Eckler's principle. For example, very little B is produced in the first of the two sequential reactions shown on the top of the next page because the conversion of A to B is endergonic. However, as the highly exergonic second reaction converts B to C, the first reaction will replenish the equilibrium concentration of B. Thus, the exergonic reaction drives the endergonic reaction. The two sequential reactions, an endergonic reaction followed by an exergonic reaction, are called coupled reactions. Coupled reactions are the thermodynamic basis of how metabolic pathways are regulated. 5.8. Calculating delta H naught values. Values of delta H naught can be calculated from bond dissociation enthalpies, as shown in the following example. The bond dissociation enthalpy is indicated by the term dH. Recall that the bond dissociation enthalpy of an pi bond of ethene is estimated to be 62 kilocalorie per mole. Because the values of delta H naught are relatively easy to calculate, organic chemists frequently evaluate reactions in terms of that quantity alone. Since delta H naught values cannot be calculated but must be experimentally determined. However, the entropy term can be ignored only if the reaction involves a small change in entropy and the temperature is low, because then the T delta S naught term will be small and the value of delta H naught will be very close to the value of delta G naught. Remember though, the many organic reactions occurs with a significant change in entropy or occur at high temperatures and so have significant T delta S naught terms. Ignoring the entropy term in such cases can lead to a wrong conclusion. It is permissible to use delta H naught values to approximate whether a reaction has a favorable equilibrium constant, but if a precise answer is needed, delta G naught value must be used. For example, because delta H naught for the addition of HBr to ethene is significantly negative, minus 22 kilocalorie per mole, we can assume that delta G naught is also negative. However, if the value of delta H naught were close to 0, we could no longer assume that delta H naught and delta G naught have the same sign. Keep in mind that the two conditions must be met to justify using delta H naught values to predict delta G naught values. First, the entropy change must be small. Second, the reaction must take place in gas phase. When reactions occur in solution, which is the case for the vast majority of organic reactions, the solvent molecules can solvate the reactants and the products. Solvation can have a large effect on both delta H naught and delta S naught. For example, in a reaction of a solvated polar reagent, the delta H naught for breaking the dipole-dipole interactions between the solvent and the reactant has to be taken into account. And in a reaction with a solvated polar product, the delta H naught for forming a dipole-dipole interactions between the solvent and the product has to be taken into account. In addition, solvation can greatly reduce the freedom of motion of the molecules, thereby affecting delta S naught. 5.9. Using delta H naught values to determine the relative stabilities of alkenes. Catalytic hydrogenation. Hydrogen adds to the double bond of an alkene in the presence of a metal catalyst to form an alkane. The most common metal catalyst is palladium, which is used as a powder absorbed on charcoal to maximize the surface area. It is referred to as palladium on carbon and is abbreviated as PD/C. The metal catalyst is required to weaken the very strong H-H bond. In addition to hydrogen to a compound is a reduction reaction. A reduction reaction increases the number of CH bonds and or decreases the number of CO, CN or CX bonds. X is a halogen. The addition of hydrogen is called hydrogenation, but hydrogenation reactions require a catalyst. They are called catalytic hydrogenations. The mechanism for catalytic hydrogenation is too complex to be easily described. We note that hydrogen is absorbed on the surface of the metal and that the alkene reacts with the metal by overlapping its p orbitals with the vacant orbital of the metal. All the bond breaking and the bond forming events occur on the surface of the metal. As the alkene product forms, it diffuses away from the metal surface. We can think of catalytic hydrogenation as occurring in the following ways. Both the HH and bond of H2 and the pi bonds of alkene break, and then the resulting hydrogen radicals add to the resulting carbon radicals. Relative stabilities of alkene. To determine the relative stabilities of alkenes, the three hydrogenation reactions shown here were carried out and their delta H0 values were experimentally determined. The heat released in a hydrogenation reaction is called the heat of hydrogenation. It is customary to give it a positive value. Hydrogenation reactions, however, are exothermic. They have negative delta H0 values, so the heat of hydrogenation is the value of delta H0 without a negative sign. The delta H0 values tell us the relative energies of the reactants and products for the three catalytic hydrogenation reactions. However, because we do not know the precise mechanism of the reaction, we cannot draw the reaction coordinate diagrams for the reactions. So we will connect the energy of the reactants and products with the dotted lines to indicate the uncertainty of the energy change that occurs between the reactants and products. The three reactions of all the same alkene products, so the energy of the product in figure 4 is the same for each reaction. The three reactions, however, have different heats of hydrogenation, so the three reactants must have different energies. For example, the alkene that releases the most heat must have the most energy to begin with. It must be the least stable of the three alkenes. In contrast, the alkene that releases the least heat must have the least energy to begin with. It must be the most stable of the three alkenes. Notice that the most stable alkene has the smallest heat of hydrogenation. If you look at the structures of the three alkene reactants in figure 5.4, you will see that the stability of the alkene increases as the number of alkyl groups bonded to the sp2 carbon increases. For example, the most stable alkene in figure 5.4 has two alkyl groups bonded to one sp2 carbon and one alkyl group bonded to the other sp2 carbon, for a total of three alkyl groups, three methyl groups bonded to its two sp2 carbons. The alkene of intermediate stability has two alkyl groups, a methyl group and an ethyl group bonded to its sp2 carbons. And the least stable of the three alkenes has only one alkyl group, an isopropyl group, bonded to an sp2 carbon. We can therefore make the following statement: the stability of an alkene increases as the number of alkene substituent bonded to its sp2 carbon increases. The more alkyl groups bonded to its sp2 carbons, the more stable the alkene is. Some students find it easier to understand this concept from the point of view of the hydrogen bonded to the sp2 carbons, namely the stability of an alkene increases as the number of hydrogen bonded to its sp2 carbon decreases. Both trans-2-butene and cis-2-butene have two alkyl groups bonded to their sp2 carbons, but the trans isomer has a smaller heat of hydrogenation. This means that the trans isomer, in which the large groups are farther apart, is more stable than the cis isomers. When large groups are on the same side of the double bond as in a cis isomer, their electron clouds can interfere with each other, causing steric strain in the molecule. Steric strain makes a compound less stable. When the large groups are on opposite sides of the double bond in a trans isomer, their electron clouds cannot interact, so there are no destabilizing steric strain. The heat of hydrogenation of cis-2-butene, in which the two alkyl groups are on the same side of the double bond, is similar to that of 2-methylpropene, in which the two alkyl groups are on the same side. The three alkenes with two alkyl groups are all less stable than an alkene with three alkyl groups, and they are all more stable than an alkene with one alkyl group. The relative stabilities of alkene that have two alkyl groups bonded to the sp2 carbons. Trans fats. Oils are liquid at room temperature because the hydrocarbon chains of their fatty acid components contain several carbon-carbon double bonds, which makes it difficult for them to pack closely together. In contrast, the hydrocarbon chains of the fatty acid components of fats have fewer double bonds, so they can pick together more closely. Because of their many double bonds, oils are said to be polyunsaturated. Some or all of the double bonds in oils can be reduced by catalytic hydrogenation. For example, margarine and shortening are prepared by hydrogenating vegetable oils such as soybean oil and safflower oil until they have the desired creamy solid consistency of butter. All the double bonds in naturally occurring fats and oily have the cis configuration. During catalytic hydrogenation, cis-trans isomerization can occur, forming what is known as a trans fat. Trans fats are a health concern because they increase LDL, the so-called bad cholesterol. Epidemiological studies have shown that an increase in the daily intake of trans fat significantly increases the incidence of cardiovascular disease. 5.10 Kinetic: how fast the product formed. Knowing that a reaction is exergonic does not tell you how fast the reaction occurs, because delta G naught describes only the difference between the stability of the reactants and the stability of the products. It does not indicate anything about the energy barrier of the reaction, which is the energy hill that has to be climbed for the reaction to be converted into products. Kinetics is the field of chemistry that studies the rate of the chemical reactions and the factors that affect those rates. The energy barriers of the reactions is called the free energy of activation. It is the difference between the free energy of the transition state and the free energy of the reactants. Delta G is equal to free energy of the transition state minus free energy of the reactants. As delta G decreases, the rate of the reaction increases. Thus, anything that makes the reactants less stable or makes the transition state more stable will make the reaction go faster. Like delta G naught, delta G has both an enthalpy component and an entropy component. Notice that any quantity that refers to the transition state is represented by a double dagger superscript. Delta G superscript is equal to delta H superscript minus TDS superscript. Delta S superscript is equal to enthalpy of the transition state minus enthalpy of the reactants. Delta S superscript is equal to entropy of the transition state minus entropy of the reactants. Some exergonic reactions have small free energies of activation and therefore can take place at room temperature. In contrast, some exergonic reactions have free energies of activation that are also large, that the reaction cannot take place unless energy is supplied in addition to the provided by the existing thermal conditions. Endergonic reactions can also have either small free energies of activation or a large free energy of activation. Let's now look at the difference between thermodynamic stability and kinetic stability. Thermodynamic stability is indicated by delta G naught. If delta G naught is negative, then the product is thermodynamically stable compared with the reactant. If delta G naught is positive, then the product is thermodynamically unstable compared with the reactant. Kinetic stability is indicated by delta G superscript. If delta G is large, then the reactant is kinetically stable because it reacts slowly. If delta G is small, then the reactant is kinetically unstable. It reacts rapidly. Similarly, if delta G for the reverse reaction is large, then the product is kinetically stable, but if it is small, then the product is kinetically unstable. Generally, when chemists use the term stability, they are referring to the thermodynamic stability. 5.11 The rate of a chemical reaction. The rate of a chemical reaction is the speed at which the reactants are converted to products. The rate of a reaction depends on the following factors. First, the number of collisions that take place between the reacting molecule in a given period of time. The rate of reaction increases as the number of collisions increases. Second, the fraction of collisions that occur with sufficient energy to get the reacting molecules over the energy barrier. If the free energy of activation is small, then more collisions will lead to reaction than if the free energy of the activation is large. Third, the fraction of collisions that occur with the proper orientation, 2-butene and HBr, will react only if the molecules collide with the hydrogen of HBr approaching the pi bond of 2-butene. If a collision occurs with the hydrogen approaching a methyl group of 2-butene, no reaction will take place regardless of the energy of the collision. Rate of reaction is equal to number of collisions per unit of time multiply fraction of sufficient energy multiply fraction of proper orientation. First point, increasing the concentration of the reactants increase the rate of the reaction because it increases the number of collisions that occur in a given period of time. Second, increasing the temperature at which the reaction is carried out also increases the rate of a reaction because it increases the kinetic energy of the molecule, which increases both the frequency of the collision in a confined space. Molecules that are moving faster collide more frequently, and the number of collisions that have sufficient energy to get the reacting molecules over the energy barrier. Third, the rate of reaction can also be increased by a catalyst. The difference between the rate of a reaction and the rate constant for a reaction. For a reaction in which reactant A is converted into product B, the rate of the reaction is proportional to the concentration of A. If the concentration of A is doubled, the rate of the reaction will double. If the concentration of A is tripled, the rate of the reaction will triple, and so on. A is converted into B. When you know the relationship between the rate of the reaction and the concentration of the reactants, you can write a law, that is rate law of the reaction. Rate is directly proportional to proportionality symbol with an equal sign if we use the proportionality constant K, which is called a rate constant. Rate is equal to K into concentration of A, where rate is equal to rate of the reaction and K is rate constant for the reaction. Do not confuse the rate constant for a reaction K with the rate of the reaction. The rate constant tells us how easy it is to reach the transition state, how easy it is to get over the energy barriers. Low energy barriers are associated with large rate constant. High energy barriers are associated with small rate constants. The rate of the reaction is a measure of the amount of product that is formed per unit of time. The preceding equations show that the rate of the product of the rate of the rate constant and the reactant concentration. So the rate of the reaction depends on concentration, whereas the rate constant is independent of concentration. Therefore, when we compare two reactions to see which one occurs more readily, we must compare their rate constants and note their concentration dependent rates of reaction. The Arrhenius equation. Although rate constants are independent of concentration, they are dependent on temperature. The Arrhenius equation relates the rate constant of a reaction to the experimental energy of activation and to the temperature at which the reaction is carried out. K is equal to A e raised to power minus EA divided by RT. In this expression, K is the rate constant, A is the frequency factor which represents the fraction of collisions that occur with the proper orientation for reaction, and E raised to power EA divided by RT is the fraction of collisions with the minimum energy, that is EA, needed for reaction. R is the gas constant, T is the temperature in kelvins, and EA is the experimental energy for activation, which is an approximate value of the activation energy. See the difference between delta G and EA on page 215. A good rule of thumb is that an increase of 10 degrees Celsius in temperature doubles the rate constant for a reaction and therefore doubles the rate of the reaction. Taking the logarithm of both sides of the Arrhenius equation, we obtain log of K is equal to log of A minus EA divided by RT. Problem 65 shows how this problem of the equation is used to calculate values of EA, delta G, delta H and delta S for a reaction. The difference between delta G and EA. The difference between the free energy of activation and delta G and the experimental energy of activation in the Arrhenius equation is the entropy component. The free energy of activation has both the enthalpy component and an entropy component, whereas the experimental energy of activation has only an enthalpy component. Because the entropy component is implicit in the A term of the Arrhenius equation, therefore EA gives only an approximate energy barrier to a reaction. The true energy barrier is given by delta G, because the energy barriers to most reactions depend on changes in both enthalpy and entropy. How are rate constants related to the equilibrium constant? The next question to consider is how the rate constant for a reaction related to the equilibrium constant. At equilibrium, the rate of the forward reaction must be equal to the rate of the reverse reaction, because the amounts of reactants and products are no longer changing. A is converted in equilibrium with B, K1 and K minus 1. Forward rate is equal to reverse rate. K1 into concentration of A is equal to K minus 1 into concentration of B. K equilibrium is equal to K1 divided by K minus 1 is equal to concentration of B divided by concentration of A. From the equation, we see that the equilibrium constant for a reaction can be determined from the relative rate constants for the forward and reverse reactions, or from the relative concentrations of the products and the reactants at equilibrium. For example, we can say that the reaction shown in figure 5.2a has an equilibrium constant significantly greater than 1, because the rate constant for the forward reaction is greater than the greater for the reverse reaction, or because the products are more stable than the reactant. 5.12. A reaction coordinate diagram describes the energy changes that take place during a reaction. We saw that the addition of HBr to 2-butene in a two-step process. In each step, the reactant passes through a transition state as they are converted into products. The structure of the transition state for each of the steps is shown on the top of the next page in brackets. The bonds that break and those that form during the course of the reaction are partially broken and partially formed in the transition state, as indicated by the dashed lines. Atoms that either become charged or lose their charge during the course of the reaction are partially charged in the transition state. Transition states are always shown in brackets with a double dagger superscript. Reaction coordinate diagram. A reaction coordinate diagram can be drawn for each step of the reaction. In the first step of the electrophilic addition reaction, the alkene is converted into a carbocation, and that is higher in energy, less stable than the reactants. The first step, therefore, is endergonic. Delta G naught is more than 0. In the second step, the carbocation reacts with the nucleophile to form a product that is lower in energy, that is more stable than the carbocation reactant. This step, therefore, is exergonic. Delta G naught is less than 0. Because the products of the first step are reactants, and for the second step, we can hook the two reactions coordinates diagram together to obtain the reaction coordinate diagram that describe the pathway for the overall reaction. The delta G naught for the overall reaction is the difference between the free energy of the final products and the free energy of the initial reactants. Transition state and intermediates. A chemical species that is a product of one step of a reaction and a reactant for the next step is called an intermediate. The carbocation intermediate formed in this reaction is too unstable to be isolated, but some reactions would have more stable intermediates that can be isolated. Transition state. In contrast, represent the highest energy structures that are involved in the reaction. They exist only fleetingly and they can never be isolated. Do not confuse transition state with intermediates. First, transition states have partially formed bonds. Second, intermediates have fully formed bonds. The figure shows that the free energy of activation for the first step of the reaction is greater than the free energy of reaction for the second step. In other words, the rate constant for the first step is smaller than the rate constant for the second step. This is what we would expect because covalent bonds must be broken in the first step, whereas no bonds are broken in the second step. The rate determining step. If a reaction has two or more steps, the step that has its transition state at the highest point on the reaction coordinate is the rate determining step or rate limiting step. The rate determining step controls the overall rate of the reaction because the overall rate cannot exceed the rate of the rate determining step. The rate determining step for the reaction of 2-butene with HBr is the first step. The addition of the proton, the electrophile, to the alkene, the nucleophile, to form the carbocation. 5.13 Catalysis. A catalyst increases the rate of the reaction by giving the reactants a new pathway to follow, one with a smaller delta G. In other words, a catalyst decreases the energy barrier that must be overcome in the process of converting the reactants to products. Figure 5.9. A catalyst provides a pathway with a lower energy barrier, but it does not change the energy of starting point, the reactants, of the energy at the end point, the products. If catalyst is going to make a reaction go faster, it must participate in the reaction. But it is not consumed or changed during the reaction because the catalyst is not used up or changed. Only a small amount of it is needed to catalyze the reaction, typically 1 to 10% of the number of the moles of reactant. In figure 5.9, that the stability of the reactants and products is the same in both the catalyzed and uncatalyzed reactions. In other words, a catalyst does not change the relative concentrations of the product and the reactants when the system reaches equilibrium. Therefore, it does not change the amount of the products formed. It only changes the rate at which it is formed. The most common catalysts are acids, bases, and nucleophiles. Acids catalyzes a reaction by giving a proton to a reactant. Bases catalyze a reaction by removing a proton from a reactant, and nucleophiles catalyze reaction by forming a new covalent bond with the reactant. We will see many examples of catalyzed reactions in the following chapters. Catalysis and the kind of species that can be used to catalyze a reaction are discussed in detail in chapter 22. 5.14 Catalysis by enzymes. Essentially, all reactions that occur in biological system are reactions of organic compounds. These reactions almost always require a catalyst. Most biological catalysts are proteins called enzymes. Enzymes are chains of amino acids linked together by covalent bonds. Each biological reaction is catalyzed by a different enzyme. Substrate, enzyme, then product. The reactant of an enzyme catalyzed reaction is called a substrate. The enzyme binds the substrate in a pocket of the enzyme called the active site. All the bond making and bond breaking steps of the reaction occurs while the substrate is bound to the active sites. Unlike non-biological catalysts, enzymes are specific for the substrate whose reaction they catalyze. All the enzymes, however, do not have the same degree of specificity. Some are specific for a single compound and will not tolerate even the slightest variation in structure, whereas some catalyzes the reaction of the family of compounds with related structures. The specificity of an enzyme for its substrate is an example of molecular recognition. The ability of one molecule to recognize another molecule as a result of intermolecular interactions. The specificity of an enzyme for its substrate results from the particular amino acids that reside at the active sites. The amino acids bind the substrate to the active sites using hydrogen bonds, London dispersion forces, the dipole-dipole interactions, the same intermolecular interactions that held molecules together. A more in-depth discussion of the interaction between the enzyme and the substrate can be found in the section 22.8. Cell wall consists of thousands of six-membered rings, molecules linked with oxygen atom. Lysozyme is an enzyme that cleaves bacterial cell walls by breaking the bond that holds the six-membered ring together. Figure 5.10 shows a portion of lysosome's active sites and some of the amino acids that bind the substrate, the cell wall, in a precise location at the active site. In addition to the amino acids that bind the substrate to the active sites, there are also amino acids at the active sites that are responsible for catalyzing the reaction. These amino acids can be acids, bases, or nucleophiles. The same kind of species that catalyzes non-biological reactions. For example, lysozyme has two catalytic groups at its active site, an acid catalyst and a nucleophilic catalyst. How these groups catalyze cleavage of the cell wall will be explained in section 22.11 after you know more about the kind of reactions that is involved.